In the current era of LLMs, we are often blinded by the massive numbers associated with context windows. We see models boasting 1 million, 2 million, or even 10 million tokens, leading developers to believe that they can simply dump entire databases into a single prompt. However, in high-stakes production environments, this brute force approach leads to a catastrophic phenomenon known as recall decay. Imagine an enterprise agent designed to enforce complex compliance rules. Even with a massive context window, the model frequently misses a specific business rule buried in the middle of a 500-page document, leading to logical loops and hallucinated responses. This isn't just a minor glitch. It is a fundamental architectural failure where the model's attention mechanism suffers from the lost in the middle effect, prioritizing the beginning and end of the input while ignoring the core. Is it just a matter of capacity, or is something deeper broken within the attention mechanism itself? The outcome of this failure is a hard lesson for many AI teams. Simply having a larger container doesn't mean the model can process everything inside it effectively. To build production-grade AI agents in 2026, we must undergo a fundamental mental model shift. We are moving away from being prompt writers who hope for the best towards becoming context architects. A context architect doesn't just pass strings. They design specialized memory components that regulate what the model sees, when it sees it, and how it remembers it over time. This involves moving beyond basic RA to more sophisticated structures like LoCoMo and long-term memory evaluations. This lecture serves as your blueprint for that transition, providing the technical rigor required to pass the most demanding system audits. By the end of this lecture, you will see why benchmarks like LoCoMo are the new North Star for these architects. Currently, most developers are just guessing, but you will be designing with precision. In the early days of 2023, prompt engineering was seen as a linguistic art form tweaking words to get a better result. Fast forward to 2026, and we are witnessing the birth of context engineering as a systemic discipline. While prompt engineering focuses on the instruction, context engineering focuses on the environment. It is the difference between giving a chef a recipe and designing the entire kitchen layout for maximum efficiency. Leading organizations now follow frameworks similar to those published by Anthropic and other research giants, where the model's entire sensory environment, including its short-term cache, long-term memory, and tool use history, is engineered for coherence. We are no longer just talking to a model. We are managing a complex information ecosystem. But treating context as just a text buffer is a rookie mistake that ignores 40 years of information management theory. Let's look at how the 2023 approach compares to the rigorous standards of 2026. From the perspective of an information management professional engineer, context must be treated as a managed data layer rather than a simple string of text. This requires architectural integrity. We must apply data governance principles to the context window, ensuring data freshness, handling redundancy, and managing the semantic density of the information we provide to the LLM. In 2026, the context layer is the most valuable real estate in your AI stack. It sits between your raw data and the model's reasoning engine, acting as a high-speed cache for intelligence. If this layer is unmanaged, the model's reasoning becomes inconsistent, leading to what we call architectural drift. By treating context as a structured stack, we ensure that the right information reaches the model at the exact millisecond it is needed. Now that we've identified the trap of long context and the need for a managed layer, we need a map to navigate the actual layers of AI memory, which is exactly what we'll build in the next chapter. In the realm of AI system architecture, we must move beyond viewing memory as a single context box. A robust agentic system requires a multi-tiered memory hierarchy similar to traditional computing stacks. At the lowest level, we have the KV cache, representing the transient instantaneous state of a single inference pass. Above this lies the session state, which tracks the immediate dialogue history and short-term reasoning traces. Finally, we reach persistent global knowledge, often stored in vector databases or knowledge graphs, which provides the agent with long-term awareness. For an information management professional engineer, the challenge is not just storage, but managing the time to live and retrieval latency across these layers. When these layers aren't synchronized, agents suffer from context fragmentation, leading to hallucinations even when the correct data is technically available. Understanding this hierarchy is the first step in moving from simple prompt engineering to sophisticated context engineering. But what happens when we try to mirror human cognitive thought patterns within this hardware-bound hierarchy? This leads us to the fundamental cognitive models of agent memory. To build agents that truly learn from interaction, we adopt cognitive science models: episodic, semantic, and procedural memory. Episodic memory captures the what and when, the specific stream of events and logs of past interactions. Semantic memory represents the know-how of facts and general world knowledge, typically handled by RAG systems. Procedural memory is arguably the most critical for 2026 agent architectures. It stores the how-to, including tool calling patterns, API sequences, and complex workflows the agent has successfully executed before. In a production environment, treating these as distinct data schemas allows for specialized retrieval strategies. For instance, episodic memory might use temporal decay functions, while semantic memory relies on dense vector embeddings. By categorizing memory this way, we can implement self-evolving agents that optimize their own procedural scripts based on episodic successes. This structured approach is what separates a generic chatbot from a professional-grade autonomous agent. Generic semantic search is failing in complex scenarios, so how do we handle the deeply personal user profiles that make an agent truly intelligent? Question, let's look at the concept of persistent personalization. The next evolution in context engineering is preference injection through persistent user profiles, similar to the memo architecture. Unlike standard RAG, which retrieves external documents, persistent user memory manages a dynamic graph of user-specific entities, preferences, and recurring constraints. In the field, we see that generic retrieval often misses the nuance of a user's specific style or past corrections. By implementing a dedicated memory layer that updates asynchronously after every interaction, the agent maintains a continuous persona. This involves an extract and update loop where the agent identifies key facts about the user such as their preference for Python over Java, or specific project naming and conventions, and stores them as high-priority context nodes. This transforms the agent from a stateless tool into a personalized partner that remembers your specific technical debt and organizational constraints. We've categorized where to store data, but the ultimate architectural debate remains. Should we just use a bigger context window or stick with external memory modules? Teaser, the answer lies in the trade-offs of latency and cost. As LM context windows expand to 1 million tokens and beyond, a dangerous misconception has emerged that external memory is obsolete. However, real-world production data from 2026 tells a different story. While long context windows are powerful, they suffer from nonlinear latency increases and significant token costs. More importantly, lost in the middle phenomena still persist. Models often fail to recall critical details buried in a 128K token prompt. External memory modules, through RAG and specialized indexing, offer a precision-first approach. They allow us to fetch only the 10 most relevant chunks, keeping the prompt clean and the cost low. In high-frequency agentic workflows, cost efficiency of external memory is the primary driver for architectural decisions. We are seeing a hybrid approach where the long context acts as working RAM and the external memory acts as the hard drive. If external memory is the winner for cost, how do we actually distill massive data into something the model can digest without losing the needle in the haystack? Question, let's examine the dynamic pruning process. To bridge the gap between massive external data and limited context, we utilize dynamic pruning ranker patterns. This isn't just about simple vector search. In 2026, the state-of-the-art involves a multi-stage pipeline. First, a coarse-grained retrieval of 100K tokens, followed by a high-precision cross-encoder or re-ranker that evaluates the semantic relevance of each segment. This process filters the data down to a highly relevant 5K or 10K token set that fits perfectly within model's attention sweet spot. We call this context distillation. For an AI architect, this pipeline is essential for maintaining accuracy in needle-in-a-haystack scenarios. By utilizing cross-encoders, we can identify nuances that a simple cosine similarity check might miss, such as temporal context or negative constraints. This architecture defines the current state of the art, but what are the industry-wide trends shaping the standalone memory market in 2026? Teaser, let's look at the final summary of the memory landscape. By 2026, memory is no longer just a feature of the LM, it has become a standalone tier in the AI stack. Industry reports highlight that the most successful agent deployments use stateful architectures where the memory layer exists independently of the model provider. This decoupling allows for model-agnostic memory, where you can switch from GPT-5 to Claude 4 without losing your agent's learned experience. We have moved from simple RAG to contextual intelligence where memory manages the agent's identity, its past failures, and its tool proficiency. This shift toward memory-first design is what enables truly autonomous agents that don't need to be retaught the same rules every session. Now that we have the architecture, how do we prove it actually works? Payoff. In the next chapter, we dive into the benchmarks that separate the toys from the tools, LoCoMo, long memoval, and the BEAM framework. Many developers believe that a high needle-in-a-haystack score translates to a reliable agentic memory, but that is a dangerous assumption. Simple retrieval is not reasoning. Long memoval is a specialized benchmark designed to measure multi-hop reasoning across session histories. It doesn't just ask if the model can find a specific fact, it tests whether the model can link a piece of information from session 1 with conflicting or complementary piece in session 10 to reach a logical conclusion. In professional AI architecture, we call this intersession coherence. If your agent can maintain this thread, it ceases to be a personal assistant and becomes a stateless chatbot. To pass long memoval, your memory system must move beyond simple vector similarity into the realm of structured knowledge graphs. This benchmark forces us to evaluate how much meaning is preserved, rather than just data stored. Question, but reasoning is only half the battle. What happens when the when of a fact matters more than the what? In dynamic real-world environments, information is rarely static. Your user's favorite coffee might change, or a project deadline might be pushed. This is where LoCoMo, or long context memory optimization and evaluation, enters the stage. LoCoMo specifically targets temporal reasoning. It challenges the model to understand the chronological validity of information. If a user said, "I live in Seoul in January and I moved to Busan in June," a naive RAG system might retrieve both and hallucinate that the user lives in both cities. LoCoMo measures the agent's ability to prioritize the most recent, valid state while maintaining the history of the transition. This is critical for building agents that act as long-term companions or reliable project managers. We are no longer just looking for a needle. We are looking for the current needle in a stack of old needles. Teaser, even with temporal awareness. How do we handle the sheer volume of a million token history? The answer lies in a different scale of benchmarking. As we move into 2026, we are seeing the rise of the 10 million token era. Standard benchmarks often fail at this scale because they don't simulate the noise and density of enterprise-level context. BEAM, or the benchmark for evaluation of agentic memory, was designed to stress test systems at this massive scale. BEAM goes beyond simple recall. It measures the memory-augmented generation quality when the context window is saturated with millions of tokens. It evaluates whether the agent can maintain a consistent personality and factual accuracy when the history is as long as a dozen novels. In the field of information management, we view BEAM as the ultimate stress test for signal-to-noise ratio management. If your architecture doesn't have a sophisticated filtering or summarization layer, BEAM will expose the resulting performance collapse. Question: with 3 heavyweights in our toolkit, how do we choose the right one for our specific agent architecture? To choose the right benchmark, we must understand the specific memory profile of our agent. If you are building a creative writing assistant, LoCoMo is your best friend because it focuses on narrative consistency. If you are building a financial advisor or a personal health coach, LoCoMo is non-negotiable because the time-to-truth relationship is critical for safety. For those building enterprise-wide knowledge agents that index entire repositories, BEAM is the gold standard for testing architecture robustness under load. This benchmark matrix allows us to move from vibe-based evaluation to engineering-grade validation. By mapping these benchmarks to your use cases, you can identify which part of your memory architecture, be it the vector DB, the caching layer, or the summarization end, needs the most optimization. Payoff: selecting the benchmark is step 1, but the real engineering nightmare begins when the agent's memory starts contradicting itself. Memory consistency is the graveyard of most LLM projects. When new information arrives, how does the model decide what to overwrite and what to keep? This process, known as knowledge updating or conflict resolution, is precisely what modern benchmarks evaluate. They measure the forgetting curve of outdated information. A high-quality memory engine should behave like a human expert. It should acknowledge the history but act on the latest valid data. In your architecture, this requires a conflict resolver component that sits between the retrieval layer and the generator. If the retriever pulls 2 conflicting facts, the system must use metadata like timestamps or source authority to resolve the tension before the LLM even sees the prompt. Question: how do we quantify this truthfulness in a way that an enterprise architect can sign off on? From the perspective of an information management professional, we don't just ask if the model is smart, we ask if its memory is governed. Reliability metrics for agent memory include precision recall of retrieved context and the truthfulness score in the face of adversarial distractors. We use a framework often referred to as the reliability quadrant. This involves testing for false positives, retrieving irrelevant info, false negatives missing key context, hallucinated links connecting unrelated facts, and stale data usage. By quantifying these metrics, we can provide a confidence score for every response the agent generates. If the memory retrieval confidence is low, the agent should proactively ask for clarification rather than guessing. This is the difference between a prototype and a production-grade AI system. Payoff: before we move to construction, let's consolidate these evaluation pillars into a single architectural blueprint. To summarize, the transition from simple RAG to context engineering is marked by the adoption of these sophisticated benchmarks. LoCoMo ensures your agent has logical depth, LoCoMo ensures it has temporal awareness, and BEAM ensures it has scalable capacity. When combined, they redefine what we mean by high-quality AI. An architect's job is not just to build a memory that stores everything, but to design a memory that curates everything. These benchmarks are your design requirements. If your system passes LoCoMo but fails LoCoMo, you have a system that knows the time but doesn't understand the story. We must balance all 3 pillars to create an agent that feels truly intelligent and consistently reliable over months of interaction. Teaser: ignoring these signals doesn't just lower quality, it creates a technical deficit that grows exponentially as your user base scales. Why does all this matter for your bottom line? Because ignoring these benchmarks leads to architectural debt. This is the hidden cost of fixing a system that was built on a foundation of poor context management. When an agent starts hallucinating due to stale memory or failing to connect dots across sessions, the fix isn't just a better prompt, it's often a total rebuild of the data pipeline. Production systems that fail these benchmarks suffer from high churn and unpredictability. By integrating LoCoMo and BEAM into your CI/CD pipeline, you catch these failures before they reach the user. We are moving toward a future where memory architecture is a standalone discipline within AI engineering. Next, now that we know how to measure the gap, let's learn how to bridge it by actually building the memory engine in our next chapter. In professional AI architecture, we must move away from simply dumping logs into a database. The state-of-the-art approach involves a reflection step, a write-through cache mechanism where the agent analyzes its own interaction before it ever hits the long-term storage. By summarizing the intent and outcome of a turn, we significantly reduce the noise that plagues long-term retrieval systems. This mimics the human process of consolidating short-term experiences into semantic memory. In 2026, benchmarks like LoCoMo specifically look for this consistency over long horizons. Without a reflection stage, your vector database becomes a graveyard of redundant, context-less fragments that confuse the model during retrieval. We are essentially building a specialized encoder that converts raw conversation into high-density knowledge tokens. This architectural choice is what separates a prototype from a production-grade agentic system. But here is the challenge. How do we handle complex, non-linear relationships that a simple list of summaries cannot capture? Traditional vector databases treat memory as a flat list of points in space, but real human context is relational. This is where graph-based memory, or what some call supermemory, becomes essential. By mapping entities and their relationships such as Project X being owned by user Y and related to document Z, we allow the agent to traverse the context like a knowledge graph. When the agent retrieves one node, it automatically gains access to adjacent nodes, providing a richer, more coherent context window. This architecture solves the fragmentation problem seen in early RAG systems where the model would find the right keyword but lack the surrounding logic. As we scale to 2020-26 standards, integrating graph RAG with vector search allows for multi-hop reasoning that flat memory simply cannot support. It transforms the memory from a mere search engine into a structured brain. This shift is radical, yet necessary for agents performing multi-step corporate tasks. But wait, how do we actually write the code that governs this complex logic? To manage these complex flows, we need a robust memory manager acting as the system harness. This component is responsible for retrieval, ranking, and most importantly, truncation. In this pseudocode, notice how the manager doesn't just fetch the top results. It applies a memory access filter, prioritizing recent events and high-relevance reflection nodes while discarding low-density noise. We implement a scoring algorithm that balances semantic similarity with temporal recency. This ensures that the agent doesn't get stuck on a detail from 3 weeks ago when a more relevant change happened yesterday. In production environments, this manager must also handle token limits dynamically, slicing the context to fit the model's Goldilocks zone, neither too empty nor too crowded. Mastering this memory access logic is the hallmark of an advanced AI architect. This code is the literal steering wheel of your agent's consciousness. But even with perfect code, how do we decide when to overwrite old memories? The answer lies in our update policies. Professional memory management requires a clear strategy for data lifecycle. Just like a traditional OS uses LRU least recently used policies, an AI agent must decide between appending, replacing, or merging information. An append policy is safe but leads to context bloat. A replace policy is efficient but risks losing nuance. The industry standard 2026 approach is the merge and refine policy, where new information triggers a re-evaluation of existing memory nodes. If the user changes their preference for a coding style, the system shouldn't just add a new rule. It should update the existing user preference node. This prevents contextual hallucination where the model sees two conflicting instructions in its own memory. This table outlines the trade-offs you must consider when designing the persistence layer of your agent. Choosing the wrong policy here is the #1 cause of long-term agent drift. Now that we have the architecture, let's look at the gold standard of guidelines provided by the industry leaders at Anthropic. Anthropic's recent engineering guides have redefined how we treat the context window. They emphasize structured I/O as the foundation of context engineering. This means every piece of retrieved memory should be wrapped in clear, XML-like tags or JSON schemas that identify its source, age, and reliability. When a model sees boda tagged memory source tungo vector DB confidence tungo 0.9 boda kun, its attention mechanism can prioritize that information over ambiguous parts of the prompt. This structured approach significantly reduces the distraction score in long memable tests. It turns a messy pile of data into a prioritized dossier. High-performance agentic context is about making the model's job as easy as possible by providing clear signposts. If your context isn't structured, you're essentially asking the LLM to do the engineering work for you, which is a recipe for failure. But structure is only half the battle. We also need to talk about density. In the world of context engineering, more is often less. We must maximize information density while minimizing noise. Information density is the ratio of decision-useful tokens to the total token count. In 2026, we've learned that feeding an LLM 100,000 tokens of raw data often results in the lost-in-the-middle phenomenon, where the model ignores the most critical facts buried in the center. Professional architects solve this by using context distillation, the process of extracting only the key semantic delta from each memory node. Instead of providing 5 similar emails, we provide one consolidated thread summary. This noise reduction isn't just about saving costs. It's about increasing the signal-to-noise ratio so the model's reasoning stays sharp and focused. Remember, every irrelevant token you include is a tax on the model's reasoning capability. If you can say it in 10 tokens, never use 100. This is the heart of engineering high-density context. But how do we know the agent is actually using the right info? The final layer of a world-class memory architecture is the verification loop. Before the agent acts on retrieved context, it must perform a self-check. Is this retrieved information relevant to the current user query? And does this memory conflict with newer facts? This retrieval verification generation, RVG, cycle ensures that the model doesn't blindly follow outdated or irrelevant data. It's like a sanity check for the agent's own memory. By asking the model to cite the specific memory nodes it used, we create an audit trail and significantly improve reliability. This closes the loop on our memory architecture, moving from passive storage to active, verified knowledge. You have now seen how to design, code, and optimize the memory of an agent, but all of this is theoretical until you put it into production. In the final chapter, we will take these architectural blueprints and map out a real-world implementation roadmap for 2026, including how to handle the specific challenges of the Korean context environment. In the enterprise sector, the shift from simple RAG to full context engineering is driven by the need for personalized consistency. Initially, most B2B SaaS platforms started with standard top K retrieval, which often led to hallucinations when users referenced past conversations. By late 2024, advanced teams began implementing incremental semantic indexing, and by 2026, we are seeing the mainstream adoption of hierarchical memory architectures. In real-world customer support deployments, transitioning to a dedicated memory layer reduced redundant queries by 40% and improved issue resolution speed by 25%. This evolution demonstrates that memory isn't just a database. It is a dynamic compression of a user's intent. As we move from stateless interactions to long-term digital twins, the architecture must support recursive context updating. However, as memory depth increases, a critical challenge emerges regarding the data stored within these persistent layers. How do we ensure that this long-term intelligence doesn't become a liability for user privacy? A significant hurdle in enterprise context engineering is privacy-aware memory. In professional environments, storing every user interaction in a long-term vector database can violate GDPR or local PE regulations if not handled properly. Architects are now implementing privacy shields, intermediary layers that utilize named entity recognition, NER, and differential privacy to scrub or anonymize sensitive data before it reaches the long-term semantic storage. This ensures that the agent remembers the lesson or context without retaining the specific sensitive data point. For instance, an agent might remember a user's preference for Python 3.12 optimization without storing the specific proprietary codebase used in that session. This architectural separation between the contextual utility and personal identifiability is the hallmark of a mature AI system. But securing the data is only half the battle. We also need to consider the physical and logical layers that make this real-time orchestration possible. What does the actual 2026 infrastructure stack look like? In 2026, the AI agent stack has matured far beyond simple API calls. At the bottom, we have the compute and foundation model layers, but the true innovation lies in the memory orchestration layer. This layer sits between the application logic and the LLM, managing the flow of short-term, episodic, and semantic memory. It utilizes LoCoMo controllers for compression and long memable for real-time quality monitoring. Enterprise-grade stacks now treat memory as a first-class citizen, similar to how we treated databases in the 2000s. We see specialized components like context cache for low-latency responses and semantic cold storage for historical insights. To manage this, architects use tools like the BEAM framework to benchmark memory retrieval efficiency against costs. This stack ensures that agents remain fast, accurate, and cost-effective even as their knowledge base grows into the petabytes. But even with the best stack, how do we evaluate if our architecture is truly working? Let's consolidate our findings into a final checklist for the modern AI architect. As we conclude this lecture, it is vital to remember that we are moving from an era of prompt engineering to context engineering. The key architectural shifts we've discussed center on treating context as a managed resource rather than an afterthought. First, memory must be hierarchical, balancing short-term speed with long-term semantic depth. Second, evaluation is no longer about simple MLU scores. It's about long context recall and LoCoMo benchmarks. Third, privacy is not a feature, but a foundation of the memory architecture. We've seen how LoCoMo allows us to compress massive contexts without losing the needle in the haystack, and how long memable provides a standardized way to measure if our agent is actually learning over time. This shift requires a mindset change from how do I write a better prompt to how do I build a better memory system. But theory is only valuable if it leads to action. How can you take these principles and audit your current AI applications today? Let's look at the final checklist. To conclude, here is your go-to-action checklist for evaluating your agent's memory health. First, you must determine if you are using RAG merely for retrieval or for true long-term memory. If you are not tracking user context drift, you are likely wasting compute. Second, ensure you are utilizing LoCoMo-style compression for long-running sessions to keep costs manageable and latency low. Third, verify that your privacy layer is properly redacting PIA before embedding. Finally, implement a continuous evaluation pipeline using the 2026 benchmarks we've discussed, specifically focusing on recall accuracy over 100K plus tokens. The transition from a stateless chatbot to a stateful, intelligent agent is the most significant leap in AI development since the transformer itself. Start your audit today by measuring your contextual recall rate. The era of the stateless LLM is officially over. Your journey into building stateful, reliable AI agents begins now. Thank you for joining this masterclass on context engineering.